Hey guys, today we're going to be talking about redox reactions, our last type of aqueous reactions. So we're going to be determining oxidation number of elements within a compound and then balancing redox reactions in acid and in base. So let's real quick go over what redox is. This is a process you're probably familiar with even if you don't realize it. Redox is a reduction or oxidation reaction, a combination of both. So it's a reduction, the re part, or read part, plus oxidation, the ox part, reaction. So it has to have both. And that's because electrons are transferred from one to the other. That transfer electrons is either going to be oxidation or reduction. So it involves the transfer of electrons. And then we call reduction a reaction where one of the substances gains electrons. So a species gains electrons. So we could either call the process reduction or we can call the reaction a reduction reaction. So the species is being reduced. The reaction where a species gains electron is the reduction reaction. Then oxidation, same idea. A species, however, is going to be losing electrons. So oxidation occurs, a loss of electrons, and then reduction occurs by gaining electrons that the species lost. So as a note, whatever electrons are lost by the oxidation half of the reaction has to be gained by the reduction half of the reaction. And here are some examples of some redox processes. Rusting, the oxidation of copper, the tarnishing of silver. It's all oxidation going on, but that oxidation is going to be going along with reducing as well. So we usually understand the oxidation process because we see that process, but there is reduction going on as well. Here's just a schematic of what's going on in a oxidation and reduction. So we've got one species who's giving up an electron to another species. That process is oxidation. And then as that accepts that electron, that is a reduction. So we're going to become more positive during oxidation because we've lost electrons, and then more negative during reduction because electrons are gained, right? Okay, so some additional terms. So oxidation, donating that electron. When a species is oxidized, it gives electrons to a species that is then reduced. So we call the species that is oxidized the reducing agent. So the reducing agent is generally the compound, or so it's the species that contains the atom that is oxidized. Okay, and I'll point that out a little bit more, but you don't generally consider the atom itself to be the reducing agent. You consider the entire species to be the reducing agent, and then you don't consider the species, the entire species, being oxidized. Just the atom within the species is oxidized. And again, I'll point that out. It's a little bit confusing right now. And then, therefore, the same idea, if something is being reduced, as it's being reduced, it's allowing the process of oxidation to occur. So the species that accepts the electrons is going to be the oxidizing agent. So the species that contains the atom that is reduced is called the oxidizing agent, as it facilitates oxidation. Okay, so we can look at the formation of sodium chloride in terms of an oxidation process. So for instance, we can have our 2 sodium, metallic sodium, reacting with chlorine gas to produce sodium chloride. And this is also going to produce a lot of heat. We can break this down into what's happening to our ions. So sodium metal is becoming sodium ions. And during that process, it's losing 2 electrons. Because of this, it is oxidation. And then the chlorine is then going to take those 2 electrons and become 2 Cl- ions. So the oxidation half produces the ions. The reduction half takes the ions. So the oxidation half produces the electrons, and then the reduction half takes the electrons. So they have to be equal amounts. A kind of mnemonic to remember this is Leo says Ger. Loss of electrons. Oxidation. Gain of electrons. Reduction. You can also use oil rig. Some people like oil rig better. Oil rig oxidation is loss. Of electrons. Reduction is gain of electrons. Okay, so let's look at what's called the oxidation state. The oxidation state will help us to kind of understand where electrons are going. So it's a tool to bookkeep our electrons. So where are electrons going? Okay, whenever a species donates or accepts electrons, its oxidation state will change. When an atom donates or gains electrons, its oxidation state or number will change. So we can see where electrons are going. As a note, oxidation states or oxidation numbers are calculated assuming that we have a purely ionic species. So assumes electron transfer during compound formation. Which is not always true. Especially in the case of covalent compounds. In the case of ionic compounds, our oxidation state or oxidation number is equivalent to our charge of our ion because it's assuming an ionic species, and that's what they are. Ionic species are ionic, so they're going to have a oxidation state equal to the charge. But if we don't have a ionic species, then we're going to have to do some assumptions that aren't going to be entirely true. Let's look at how we would determine our oxidation state of an atom within a compound molecule or element. So you're going to follow these step by step to determine all the oxidation states of all the atoms that are involved in the reaction itself. Most of the times, your oxidation states will remain the same on each side, but not always. So you need to do it for every single atom. Okay, so first elemental state atoms will have an oxidation state, which I'm going to start abbreviating as OS, of 0. So stuff like H2, Br2, sodium metal, iron metal, carbon solid. So things in their elemental form, their oxidation states, the atoms within there will have a 0 oxidation state. In ionic compounds, the oxidation state will equal the ion charges. So, for instance, sodium chloride has sodium ions and chlorine ions. So sodium, in this case, would be a +1 oxidation state. Chlorine, in this case, a -1 oxidation state. We do have, on occasion, some monatomic ions that aren't ionic in nature. But here, again, our oxidation state will equal the ion charge. Such as an H+ ion, the oxidation state here would be +1. We also have a hydride, which would be -1. If we have nonmetals, they will usually have negative oxidation states, but not always. So the order that we're going to be determining our oxidation states is first, hydrogen will be +1 if it is attached to a nonmetal, -1 if it's attached to a metal. Okay. Next is oxygen, and it has an oxidation state equal to -2 unless it is a peroxide. So something that contains O2 2-, at which point it's going to have a -1 oxidation state. Okay. Next. Halogens are going to have -1 oxidation state. Unless preceded by one of the rules before it. Okay. And then as a note, the sum of the oxidation states will be equal to the charge on the species. So any covalent species is going to have a sum of 0. Any charged species will be equal to the sum of the charge on that ion. So let's try this out. We have H2S. So following down our rules, the first rule that we see is for hydrogen. And hydrogen is going to be in a covalent species +1. So if this is +1, each hydrogen is +1, then this portion of the molecule is +2. It's a neutral species, so overall it has to be 0, so the sulfur has to be -2. And that's all we do. We do the ones that we know, and then once we've run out of ones we know, the oxidation state of, or when we get to our last species, basically, we are going to assign it based on just arithmetic. S8, this is sulfur in its elemental form, so sulfur is going to be 0. SCl2, chlorine is going to take precedence over here. So chlorine is a halogen, so it's -1. So each one of these chlorines is -1, so this half is -2, which meaning that half has to be +2. Sulfur. Sodium sulfite. Here we have 2 ions, so I'm actually going to do this over here. We have sodium ions and sulfite ions. Right? So sodium is going to be +1. Sulfite, we're going to have to break it apart. So oxygen is -2. There are 3 of them, so this portion is -6. The whole thing has a charge of -2, so sulfur has to be +4. So our oxygen, each of them are -2, even though there are 3 of them that sum to -6. One oxygen has a oxidation state of a -2, so just write the oxidation state for one of the oxygens. And then sulfur is going to be +4. Okay. Then we have the same idea here. We have sulfur and oxygen together, and it's a polyatomic, so this is our sulfate. So we have sulfur and oxygen. This portion of the molecule, each oxygen is -2. So that portion is -8. We have a overall -2. In order to get to a -2 with -8, we need to add 6. So our sulfur is a +6. Okay. So just systematically go through, do the ones you know, and then you should have one left at the end, one atom left at the end that you need to solve for the oxidation state for, and you're just going to use simple arithmetic where your oxidation states are going to sum to equal the charge of your atom. Your oxidation states are going to sum to the charge of your molecule or your compound or your molecular ion. So just keep that in mind. Okay, so when we have a metal, metals can be oxidized by acids or salts. Okay, and the general reaction is we have some metal. It's going to react with BX, where BX could be a salt or it can be an acid. And when it does that, it's going to produce a metal salt and some other species. Okay, so we can look at magnesium, for instance. Magnesium solid. When we react it with hydrochloric acid, it's going to produce magnesium chloride and hydrogen gas. We can also take magnesium and react it with a salt, such as manganese chloride. And when we do that, we'll produce magnesium chloride and manganese. Okay. Now, Depending on which metal is oxidized, which one is reduced, will be dependent upon our activity series. So our activity series tells how oxidizable or reducible an atom or ion is. Okay, so redox reactions can be broken down into the reduction and oxidation halves. Okay, so if we have, for instance, this one right here, we could write this as Mg goes to Mg2 plus 2 electrons, and then H plus 2 electrons goes to H2. So this would be our oxidation and our reduction halves. Okay, so let's actually look at our activity series, what determines how things are going to be oxidized or reduced. So this is a list of metals and their half reactions. And this is going to be arranged in order of decreasing ease of oxidation or increasing ability to take an electron or be reduced. So at the very top, these are going to be things that are very, 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 very easy to oxidize. And then their flip reaction is going to be very, very hard to reduce. So lithium, as we know, being an alkali metal, is very reactive and does not want to be in an elemental form. So it very easily oxidizes. Going down here, we look at gold. Gold, on the other hand, is very, very hard to oxidize, which is why it's a precious metal. Platinum's down here as well, and silver, and copper. Right? Things that are very hard to oxidize. So things that don't oxidize very easily stay shiny and pretty. Mercury is not a precious metal or a noble metal because it's a liquid, so they don't really use that to make jewelry out of. But the rest of them they use to make jewelry out of or wire out of because of how hard it is to tarnish or oxidize them. On the other hand, Au3 plus 3 electrons going to Au solid, very easy to do. This is a very simple reaction. It has a very high reduction potential. Okay, so at the top, we have very high oxidation potentials. At the bottom, we have very high reduction potentials, so we can very easily reduce species. Okay, so keep that in mind when you're trying to think about the direction that you want a reaction to go when you're trying to determine if it will or won't go. So you basically, if you want the top, if you want something to occur, you need to have the oxidation half be above the reduction half. So we could oxidize lithium and reduce potassium. Or we could oxidize magnesium and reduce chromium. So what I'm meaning is if we have lithium solid plus K plus going to lithium plus and K solid, this is easier to oxidize, this is easier to reduce, so they will form together a reaction. If we want to do the magnesium one, we could do magnesium solid plus chromium 3 plus going to magnesium 2 plus and chromium solid. We just need to balance that out like so. but that would still work out because this is easier to oxidize, this is easier to reduce. Okay, so balancing simple redox reactions is very simple. You're going to write the oxidation and reduction halves reactions, and then you're going to add electrons in to balance everything out, and then you're going to multiply them to make sure the electrons are the same on both sides and add the two equations together, canceling out the electrons. So break apart into oxidation and reduction halves. Then you add electrons to balance. Then balance electrons between the two halves. And then you combine equations, canceling out their reaction, canceling out the electrons. Easy peasy. A note about simple redox balancing. If we have ionic species, we're going to use the ions and ion charges only. You can kind of ignore any additional things and bring them back later. So for instance, if we have magnesium plus iron 3 sulfate, going to magnesium sulfate and iron. So with this, we can just break it down into ions, basically. We've got our magnesium going to magnesium 2 plus, and we've got our iron 3 plus, two of them, going to iron solid. And obviously, there's going to be two there as well. And then we put in electrons. On the first one, we have a 0 charge on the left side, 2 plus charge on the right side, so we're going to add 2 electrons. In the other one, the iron one, so I'm going to move just a little bit over. We have a 6 plus on the left side, 0 on the right, so we're going to add 6 electrons on the left side to balance out that charge. Then we want to balance the two equations. They both have to have the same number of electrons. So we multiply this one by 3. This gives us 3mg goes to 3mg2 plus 6 electrons. And then we combine the two equations, canceling out our electrons, which should cancel out. And we get 3mg plus 2fe3 plus goes to 3mg2 plus 2fe solid. And then we could put our counter ions back in. 3mg plus Fe2SO4 3 goes to 3mg SO4 plus 2Fe. Easy peasy. If we have nonmetals, we have to look at our oxidation states. So if we have nonmetals, changing oxidation states. Much more complicated. But we will look at that in this video. So let's just practice some simple ones first. So we have tin and silver coming together. So tin and then silver. So we'd write our two halves. We have Sn2 plus going to Sn, and then silver going to silver plus. Balance out our charges, and then balance out our species, and we get 2Ag goes to 2Ag plus 2 electrons, and then we can combine the two, giving us, as we combine them, Sn2 plus 2Ag goes to Sn plus 2Ag plus. Here we have polyatomics, so we're just going to ignore them for this first part. So we have Ag plus going to Ag, and we have Cu going to Cu plus. An electron here, and electron here. They're the same in both cases, so we can just combine them directly. Ag plus Cu goes to Ag plus Cu plus, canceling out those electrons, and then we'll put back in our counterions. AgNO3 plus Cu goes to CuNO3 plus Ag. So we didn't actually do anything to that one. It's not very common, but I just wanted to show it to you. So now let's look at our steps for balancing redox reactions that aren't simple. So when we're balancing in aqueous medium, either acidic or basic in nature, we have a lot more steps. So first thing we want to do is we want to separate into reduction and oxidation halves like we did before. Then we're going to balance the elements other than oxygen and hydrogen. Okay, so any other elements besides oxygen and hydrogen, we can balance them directly just using regular stoichiometry. Then we're going to balance oxygen atoms by adding in water. So add in the appropriate number of water molecules. If we have one extra oxygen atom on one side, you'll add one extra water molecule on the other side. Next, we're going to balance hydrogen atoms by adding H plus ions. Okay, same idea, but one for one again here. Now we're just adding in charges. Then you're going to add up the charges on each side and make them equal by adding electrons to the more positive side. Rule of thumb, side that has H plus ions, generally going to be the side that has the electrons on them. Then you're going to make sure the electrons on both sides of the equation are equal. If they're not equal, then you multiply by the appropriate integer to make sure that they are, so the lowest common multiple. And then you're going to add the two half equations together, making sure to cancel out electrons and any other things that show up on both sides. And then you're going to form one balanced equation. Now, if you are in acidic medium, you are done. However, if you are in a basic medium, we can't have a bunch of H plus ions in a basic solution. So we're going to cancel out the H plus ions by adding the appropriate number of hydroxides. So however many H plus ions you have, it's supposed to be hydroxide, uppercase, however many H plus ions you have, you're going to add that many hydroxides to both sides of the equation. Both sides. Very important. Then you're going to check and balance again. Let's try a little redox practice. So this first one's pretty simple. We have H2 plus O2 going to H2O. So we're going to break this apart into our two halves. We don't know which half is which, but that's okay. So we have H2 going to H2O. And then we have O2 going to H2O. That's perfectly fine. On our left one, we're going to balance out our oxygens first by adding in water. Looks weird, I know. And then we're going to add two H plus ions to balance out our hydrogens, and then 2 electrons to balance out our charge. On our other side, we're going to add a 2 here to balance out our oxygens. Then we're going to add 4 H plus ions and 4 electrons. So our left half is giving up 2 electrons. Our right half is taking 4 electrons, so we need to multiply this by 2. This gives us 2H2O plus 2H2 goes to 2H2O plus 4H plus 4 electrons. We can now combine the two equations, canceling out anything that's the same on both sides. So we're going to cancel out these waters, these electrons, and these H plus ions, giving us 2H2 plus O2 goes to 2H2O. Some notes about this. The hydrogen half is producing electrons, so this is oxidation. And it's the hydrogen is oxidized. Right? And then the other half is reduction, where oxygen is reduced. So we would say that H2, the actual species that contains what we're looking at, is going to be the reducing agent. And then O2 is the oxidizing agent. Okay, so the atom is what's being oxidized and reduced. The thing that contains the atom is the thing that's the agent. Let's try a little bit more complicated of an example. Okay, let's try our next example. We've got copper plus nitrogen dioxide going to copper 2 plus our nitrate ion and nitrogen monoxide. Whenever we're bringing a redox reaction into the reduction and oxidation halves, try and make sure you get all of the components. And you're basically looking at what's changing. So what is being changed? We can figure that out using oxidation states. So our copper is changing oxidation state, and so is our nitrogen. So we want to go ahead and include everything that has nitrogen in it, as that's the thing that's going to be changing oxidation state. So our two halves are going to be copper, goes to copper 2 plus, and then nitrogen dioxide goes to our nitrate ion and nitrogen monoxide. Okay, we need to balance each of these out. Our left equation, copper going to copper 2 plus, our atoms are already balanced. We just need to add electrons to balance out our charge. Left side is 0 charge, right side is 2 plus, so we need to add 2 electrons to get them both to a 0 charge. And then our right one, first our atoms are going to be balanced and then our charge. So we want to look at any element besides oxygen or hydrogen first, and that gives us nitrogen in this case. Nitrogen is not balanced. There are 2 nitrogens on the right side. The left side only has 1, so we need to add a 2 in front of the nitrogen dioxide. Then we're going to look at our oxygens. If we look, there's 4 oxygens on the left, 4 oxygens on the right. We're balanced there. And now we just need to add in electrons to balance the charge. The left side of our reaction has a 0 charge. The right side has a -1. So we need to add 1 electron to our left side to get a -1 charge on both sides. Now, our oxidation half, the one that's producing electrons, has 2 electrons. The reduction half, the one that's taking the electrons, only has 1, so we need to multiply our reduction half by 2, giving us 2 electrons plus 4 nitrogen dioxide molecules, goes to 2 nitrate ions and 2 nitrogen monoxide molecules. We'll then combine the 2 equations, canceling out anything that's the same on both sides. Only thing that's similar between the two are the electrons, and they should always cancel out completely. And then we combine the 2 equations to give us copper plus 4 nitrogen dioxide molecules goes to copper 2 plus 2 nitrate ions plus 2 nitrogen monoxide molecules, and we have a balanced equation. So next thing I want to do real quick is just looking at what's changing. So our copper is changing oxidation state, so it is being oxidized. And it's also our reducing agent in this case because it's not part of a compound. Our nitrogen is what's being reduced. So nitrogen is part of a compound, so NO2 would be our oxidizing agent. And that's balancing 2 examples in acid. If we are in a base, it's a little bit more difficult. So let's try this one out. I'm going to go here, 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 here. So we have H3PO2 going to H3PO4. And we have Cr2O7, 2 minus, going to Cr3 plus. So first, anything besides oxygen and hydrogen, we're good on the first one. Next, we need to do oxygen. So we need to add 2 H2Os this side. So we have 4 oxygens on the left side, 4 oxygens on the right side. Now we have an imbalance of our hydrogens, so we need to add 4 H pluses to the right side. Now an imbalance of our charge, we have 0 on the left, plus 4 on our right, so we add 4 electrons to our right side to balance that out. Let's go to our bottom one, balance out our chromium first, then we add in 7 waters to balance out our oxygen, and then we add in 14 H plus ions to balance out our hydrogens, and then we need to balance our charge. The left side has a plus 12 charge, 14 here, and then we subtract minus 2 there. And then our right side has a plus 6. So in order to balance this out, we need to add 6 electrons to this side, like so. So now our left side is plus 6, our right side is plus 6, and we are balanced. We have 4 electrons being produced in this oxidation half, and then 6 electrons being consumed in this reduction half. So we need to multiply this by 2. We need to multiply this by 3, and we get 6 H2O plus 3 H3PO2 goes to 3 H3PO4 plus 12 H plus 12 electrons. And then we have 12 electrons plus 28 H plus ions plus 2 dichromate ions going to 4 chromium 3 plus ions and 14 water molecules. We'll now combine the 2 equations. We want to combine this equation with this equation. Just they're separated by a little distance, so I just want to put that in there. We have 6 waters, those will completely cancel. And we'll remove 6 from here, so that will give us 8. We have 12 electrons, those will cancel. We have 12 H plus ions, those will completely cancel out. And then we'll remove 12 from there, which gives us 16 H plus ions here. And that should be all of it, yep. So now, after we're done with this, we're going to combine the 2. We have 16 H plus and 3 H3PO2 plus 2 Cr2O7 2 minus goes to 3 H3PO4 plus 4 Cr3 plus 8 waters. Now, this is in basic solution, so we have to add hydroxide ions equal to our number of H plus ions. So we're going to add 16 hydroxide ions to both sides. When we do that, these will combine. So 16H plus 16OH minus gives us 16 waters, just acid-base reaction. Those 16 waters are then going to cancel out with these 8 waters to give us 8 waters on this side. And what we get is 8 waters plus 3 H3PO2 plus 2 Cr2O7 2 minus plus 3 H3PO4 plus 4 Cr3 plus 16 OH minus. You can verify and make sure your charges, they should be the same on both sides. Each element should be the same on both sides. So everything should balance completely at the end of this. And we can check that. I'm not going to, but I would encourage you to go through and make sure that you're getting the same numbers on both sides. Another note that I would like to make is just going through and making sure you know what all the species are. So the thing that has the species that is being oxidized is our reducing agent. So what's actually being oxidized in the species? It's going to be our phosphorus. And we can verify that with oxidation states if you don't see it right away. But our phosphorus is going to be oxidized, and then chromium is going to be reduced. So we'd say phosphorus is oxidized, and then our H3 PO2, H3PO2 is our reducing agent. And then chromium is reduced. And then our Cr2O72- is our oxidizing agent. So you should be able to balance these. You should be able to recognize what's being oxidized, what's being reduced, which is your oxidation half, which is your reduction half, which is your reducing agent, which is your oxidizing agent. And that is finally everything.